Okay, so yeah, today we are going to see some applications and motivations of matching. So, okay, so just to recall, so we define matchings as a set of disjoint edges. So, let's say you have some graph here, then typically a matching would look like this. So this is a valid matching, but if you add, let's say, this edge, it is not a valid matching because these this edge and this edge, they intersect in a vertex. So matchings is basically a set of um, disjoint edges. And yeah, and we define what is the size of matching. So size of matching is basically the number of edges. So okay, so in this case, just as an example, so in this case, what is the maximum size of a matching that you can find? Is it, yeah, yeah. So you're right, Amjad. So this in this case, you can the maximum size of a matching is 2. So yeah. So what we want to do now is we'll quickly see what all applications there are. So this is definitely something that we come across in everyday examples, but just that we don't explicitly make a point. So yeah. So let's take as first example. It's called. So let's define this problem, which is hostel room allocation problem. So on one side, you have students, and on the other side, you have, let's say, a set of rooms. So let's say uh, these are a bunch of students who have newly come to a college, and yeah, and they're going to be allocated some rooms in the hostel. And now the thing is, we're going to ask them for preferences. So let's say Amjad prefers room 1. Say it has a nice view, so Amjad prefers room 1. Then let's say Vivek also prefers room 1. Let's say Tulsi prefers room 3, and so on. So you have, so number of rooms and all is not a constraint for us right now. So likewise, for every student here, you have some preference of rooms that they have. So what do we want to do? We want to uh, assign one room to each student, such that uh, they're they're satisfied with it. So what do we mean by that? So let's say that X is happy if X gets their preferred room. Okay, otherwise we say that the that X is unhappy. Okay, so is it possible for us to always come up with such a assignment that everybody is happy? So what do you think? Yeah, no. So that's right. So why is that? One example is right here. So in this case, Amjad and Vivek, they both prefer room 1, but we can't assign the same room to both of them. So either Amjad or Vivek will end up getting unhappy. So it is not possible to make everybody happy, but what is it that we can do? We can try to make as many people happy as possible. So our goal is to maximize the number of happy people. So Yeah, so any ideas how do we do that? Okay, so let's say that Amjad gets room 1. Okay, so let us denote it by this blue edge, and let's say Tulisi gets this blue room, this room 3, and so on. So, and similarly, you have other assignments for everyone. So, yeah, so what we are trying to do is we are trying to maximize the number of edges that we can pick from this. So, that is exactly what a maximum matching is. So, this is nothing but this is same as finding maximum matching in the graph G, that is this. So is this okay? So this is a matching because clearly this is a matching because one person here can only get room 1 and the other way around, and we are looking for a maximum matching in the sense we are trying to pick as many black edges from here as possible. So that is same as finding the maximum matching. So is this okay?
Yes.
Okay, so this kind of situation occurs very often. So yeah, so there are lots of examples that are there everywhere around, and these kinds of matching algorithms is what people use to yeah, to basically find a good enough solution. So we can't find the best solution because, like we said, in this case it's not possible to make everyone happy, but there is a certain parameter that we are trying to maximize. So okay, yeah. Yeah, so just on that note, yesterday we saw an algorithm for maximum matching. I mean, we did not look into the details of the algorithm, but we just said that there is a Edmonds algorithm, um, yeah, which runs in polynomial time. So we basically use this as a black box, and we did not do details of this. So there was this other approach that was proposed by Yadu. I just yeah, I'll just bring it up. So yeah, so the idea was that you pick up an edge which has minimum degree and you remove all the edges. So pick an edge with minimum degree. So okay, so I mean, I'm assuming that degree of by degree of edge we meant the sum of degrees of the two vertices and so on, and you delete the edges incident on, let's say, E, and then you repeat the process. So this was the algorithm. This is a greedy strategy. So okay, so I uh, yeah, so I think this is a counter example for this. So let me know if this is fine with you. So okay, so basically the idea is that you take an odd length path, and now yeah, so now there are two matchings that you can see here. One is that you pick this edge, and the other is that you pick these edges. So this is what you would want to do, but because your algorithm says that yeah, because your algorithm says that you want to pick the edge with minimum degree first. So what I'm going to do is I'm purposefully going to make the degree of these vertices large. Okay, so I'm going to modify this graph as follows. Okay, so the final graph that we have looks like this. Okay, so in this case, if you run the greedy approach, then what would the algorithm do? If you look at this edge, yeah, so the degree of this vertex here and this vertex here is minimum, it's only degree 2. So it would, let's say, end up picking this edge, then you can't pick this edge and you can't pick this edge. Similarly, yeah, then let's say you pick this, then you can't pick the other two, and same thing happens here. So in this case you end up getting a matching of size 3, which is by the greedy approach, but a maximum matching here would look like this. So that's something I thought would be a counter example to the approach. So is it fine?
Yes, yes.
Okay, so yeah, so yeah, I just wanted to yeah, bring it up now. Yeah, so we saw this example of hostel room allocation where um, okay, where these let's say you tell that this is the room that you want, and what happens if you uh, I mean, okay, so maybe I'll take a new page. Okay, so okay, so let's say Amjad prefers room 1 and Tulsi prefers room 3, but uh, but let's say that the matching that you have, like there is some algorithm that outputs some matching, and what it does is it instead um, gives assigns room 3 to Amjad and assigns room 1 to Tulsi. So this is not a good matching. So M is not, okay, let's say M is a bad matching for us, because yeah, because simply because uh, Amjad would prefer room 1 over the room that is assigned to him, and Tulsi would prefer room 3 over what is assigned to her. So in this case they can simply swap their rooms and they both can be happier. So instead what you do is you swap their rooms and they would both end up being happier. So this kind of situation that happens where there are two people here who are happy to exchange their assignments rather than staying with the current assignment. So these kind of situations that happen, these are called instabilities in the matching. And if there is an instability, then it's a bad matching, because there is a better way of allocating where there are more people who are happy. So this is exactly what we want to avoid. Okay, so yeah, so is this okay?
Yes.
Okay,
Yes, ma'am.
okay, good. So let's look at the third. Okay, there are a lot of people here, and I'm just looking at a few of them. So let's look at Vivek. So what happens to him? So if Amjad gets room 1, then he would end up getting some other room that, I mean, we don't know how the matching works, but he will end up getting some other room that he may or may not like. So in that case, what we do is that in general you don't have specific, like you don't just have one preference. Okay, this is what I want and that's all, and that's all. You generally have a lot of options. So you have that this is the room that I prefer the most. If I don't get that, then maybe there is some other room that I prefer the most, and if I can't get even that, then maybe there's something else. So you generally have a list of preferences in some order. So let's say Amjad prefers, let's say, room 1 the most, but if he can't get 1, then maybe he would be happier if he gets 5. If he can't even get 5, then maybe he's okay with 4, and so on. So this kind of what this kind of preference list allows us to do is that instead of randomly, in the worst case, if you can't get 1, then rather than getting some random choice, it's better if I can give you a preference list so that you can try to give me as better choice as possible. So this would definitely end up making the students happier. So let's consider matchings like that. So in this case you have students and you have rooms, but this time each student has their own preferences. So there is some ordering for each of them. And what is our goal this time? We want to minimize, uh, yeah, so instead of simply keeping a binary value for happy and unhappy, so if the person gets the most preferred room, we said he's happy, otherwise he's unhappy. So instead of doing that, instead of keeping it binary, maybe we will keep some happiness quotient. So if a person gets the most preferred room, then let's say the happiness quotient is, or let me call it unhappiness quotient for per student. So if he gets the most preferred room, let's say the unhappiness is 0. If he gets the second preferred room, then it's say 1, and so on. So you have some weights assigned to it. And what is the goal? So anybody, what is the goal that the matching should, I mean, we would want to achieve? Okay, so yeah, so we want to minimize the sum of, let's say u of x denotes the unhappiness of student x, then we want to minimize the total unhappiness. So we can't end up in a situation where everybody's is as happy as possible or as less unhappy as possible, but we are globally trying to minimize the unhappiness. So that is the goal that we have. So the same algorithm of finding maximum matchings that we have will not directly work here, because now you have other constraints to take care of. So yeah, but this is one kind of situation that typically arises, and there are efficient algorithms for this. And I think there are lots of codes also that are written on this, and you can check it out or you can try to code it yourself. But yeah, so we'll not look into the algorithm for this, but there are good polytime algorithms for this situation as well. So yeah, so what we um, what we did here is basically that you had students and you had rooms, and students had preferences, but the rooms don't have preferences. It doesn't make sense to say that. So these kinds of situations, these are called one-sided preference matching. So here there's only one party that has preferences. Now the other kind of situation that arises is what is called quota. So in the previous case, what we said is that each room has a capacity of accommodating one person. But let's say now the situation is different. Let's say that uh, there are two occupancy rooms, three, and so on. So let's say that room number 1 has a capacity of accommodating 3 people, room 2 has a capacity of 3, and let's say room 3 has 1, and so on. So now it is possible, like in the previous case, in the previous case either Amjad or Vivek ended up being unhappy. But in this case, since room 1 has a capacity of 2, they can both end up sharing room 1 if they prefer that. So yeah, so these kind of quotas also come up very naturally. So yeah, so these kinds of situations are called one-sided quotas. Okay, so one example that you yeah, that is very relevant is your JOSA allocation. So if you give this exams and you are applying for colleges, JOSA uses some matching algorithm. So here you have students who have their preference list. So let's say student 1 prefers, let's say IIT Bombay, somebody prefers NIT Calicut or something. These are some preferences that the students have. And on this side you have colleges. Okay, and the colleges have limit on how many students they can accept. So each college will say, so maybe IIT Bombay will say that I have a cap of 100 students, or let's say they have a cap of 150, and so on. So yeah, so these kind of situations where you have preferences on one side, these are one-sided preferences and one-sided quotas. So these kind of situations also arise very commonly, and they indeed do use these matching algorithms to find matching where uh, as many people end up getting happy as possible. So yeah, so they yeah, so that is definitely one situation that occurs. And yeah, can you think of a situation where there are two-sided quotas?
Situation in which college prefer score.
College prefers
Rank of the student.
oh no, sorry, I did not understand.
In this situation, college prefers the rank of student and the student prefers any college
Okay.
according.
Okay, so the situation that you are saying is with two-sided preferences, where students also have preferences and college also has preferences. So yeah, that is correct. Can you think of two-sided quotas? By quota, I mean that they have some capacities. So let's say IIT Bombay can accommodate only 100 students and so on. Okay, so one example um, would be course allocation. So let's say there are students here, and there is each student has some quota of courses that they need to take. So let's say this student A has to take four elective courses in this semester. So that is the minimum number of courses he or she has to take. And the courses that he prefers are, yeah let's say this C1, C2 and C5. Let's say he's okay with, or okay, there are a lot of, let's say he has certain courses that he's okay with taking. And similarly, every other student have some number of courses they need to take, and they have some preferences for the courses. Okay, so but at the same time, a course cannot accommodate any number of students. So there may be 100 students that are willing to take course C2, but the course cannot handle that many students. So maybe they also have some quota. So this course maybe just allocates can only allow 30 students. Let's say C5 can only allow 42 students, and so on. So in this case, students also have some quota that they want to do these many courses, and the courses also have quota that they can only take these many students. So yeah, so that is one example, that one such case that arises. And yeah, you were right about the preferences thing. So if you want double sided preferences, then uh, you can think of colleges wanting to admit students with more rank. And yeah, so yeah, so is this okay with everyone?
Yes.
Okay, so okay, so I'll take one example where this two-sided preferences occur. So I'll show you one video, and if there is time, we will discuss the algorithm. So okay. Okay. So is the screen visible?
Yes.
I'm going to play the role of a yenta. So let's say I live in a remote village and there are a bunch of young men and a bunch of young women, and it's in the village's interest that everybody gets married, everybody pairs off. We're only talking about heterosexual marriages today. That's actually really important to the mathematics, but let's leave that aside for now. And I get to arrange the marriages. I get to choose. I know all the young men and young women very well. I know what their preferences are, but it's really ultimately up to me. And my ultimate goal, my principal goal in arranging these marriages is stability. So I don't mean stability over time. People might grow apart, their preferences might change. But I mean instead the following scenario. Say I've arranged a marriage between this couple here, so this young man and this young woman. And then I've arranged another marriage here for another couple, another man, another woman. But suppose this woman prefers this man to the husband that I've assigned her, and this man simultaneously prefers this woman to his wife that I've assigned.
That's not good.
That's not good. That means that these two are going to say, to hell with this arrangement, and run off together. So that's what we want to avoid. So I'll say this situation is not stable. And then the question today is it possible, is it always possible to arrange stable marriages? So I want this.
Um, okay, so I'll share the link of the sorry yeah I'll share the link of that video to you on the group later after the class. So let me just explain what the problem was. So this is typically inspired by the old tradition of Swayamvar. So basically, you have a list of women here, and you have a list of men here. Okay, and yeah, and each of them have some preferences. So let's say, um, let's say this woman W1, she prefers M2 over man 3, and so on. So there is some preference for this woman, and similarly the man has some preferences, so maybe W4 over W3 and so on. So these are two-sided preferences, and what you want to do is you want to end up uh, making matchings. So at the end you want to output something like this. So maybe W1 is maybe W2 is married to M1, and the let's say W4 is married to M7, and so on. So at the end, furthermore, let's assume that there are exactly n women and n men, so there's no question of somebody remaining single. So we want to marry each woman to some man and the other way around. Okay, but we want to take care of the preferences, so we want to make yeah okay. So this kind of situation happened earlier also in the in the room allocation. So if let's say Amjad preferred room 1 over and Tulsi preferred room 3, then it would be unstable if you allocate the room 1 to Tulsi and allocate room 3 to Amjad. So that is instability in terms of rooms. Similarly, there is instability in terms of marriages. So how is that? So let's say W1 is married to M1 and W2 is married to M2, but let's say that W2 prefers M1 over M2 and the man 1 prefers woman 2 over woman 1, then they would be happy to swap. So it would be a happier marriage if M1 were mapped to were assigned to W2, and the other way around. So this would have been a more stable situation, because at this point M1 is also willing to swap and W2 is also willing to swap. So they would be in a happier state if the matching was changed. So these kinds of situations that happen in case of this marriage problem, so these are called instabilities. Okay, so again the idea is same. We want to remove all the instabilities that can arise. So basically we want to find a stable marriage. Okay, so is the question clear? So you have n men and n women on both sides. Each of them have their own preferences, and at the end we want to uh, end up matching them such that there are no instabilities. So that is the goal. So yeah, if you want to take some time and think about how to proceed about this, I'll wait for a couple of minutes. Yeah, but if there are any questions about the problem, ask me. Okay, so let's see one way of doing this. So the reason why I wanted to talk about this problem, so this is called the stable marriage problem. Okay, so the reason I wanted to talk about this problem is because the kind of algorithm that is there is very different from all the paradigms that you might have seen so far. So you might have seen this greedy strategies, dynamic strategies, and so on. But the kind of approach the algorithm takes is very different from what you have seen, and it's not very difficult. Also, it's kind of easy to state, but it's very non-intuitive. So that's why I wanted to discuss this. So just a little bit of history about this. So the first algorithm for this was given by two people called Gale and Shapley, and they published a paper in 1963 called College Admissions and Stability in Marriage. Okay, so yeah, so what happened is um, during the 1960s, people in America, um, they came across one issue that there were students from um, yeah, there were students from medical colleges who had done their MBAs and all, and now they wanted to practice into hospitals. So these are medical students, and they were looking for hospitals to apply to. At the same time, hospitals were looking for students to come in and so on. So the students had their own preferences and the hospitals had their own preferences of students, and now the problem was how do we assign them so that it's not too unfair. So there was no way of assigning at the time, and mostly it was close to uh, arbitrary assignments, and that ended up in a situation where people were not very happy. So these people came up with a matching algorithm. So this is called national resident matching. So for this algorithm that they gave, they received a Nobel in economics. And by that I don't mean just for this algorithm. There is a series of works they did, and this was one of them. So this was quite a great result. In fact, this is the first time people came across this matching algorithm. So this is the first time this thing came up, and later on we started to realize that these situations arise more often. And we look for algorithms that are more suitable for the specific situation that we have. So I'll just describe their algorithm quickly. So their algorithm, okay, so in this case, just think of these medical students as women and the hospital. Okay, I mean, it's a similar situation, just that the sets are the sets are labeled differently. So let's describe the algorithm. So so what happens is that uh, a woman looks at her list. Let's say W1. She looks at her list of preferences. So let's say she prefers M3 over M2 over M1. Okay, then she goes and proposes to the first man that is in the preference list. So what I mean by this has not yet proposed to. I'll explain this later. Basically, it's that she's going to keep on proposing in the order. So if M3 rejects for some reason, then she'll next time she'll propose to M2 and so on. So it's never going to happen that the same person gets the proposal again. So that's what we mean by it. And what does a man do? So when a man gets a proposal. Okay, so there are two possibilities. One is that maybe a man gets a proposal and he's single, so he's not yet matched to anyone, or it is possible that he is matched to someone. So if he's not matched to anyone, if single, then he accepts. And if he's matched already, so matched, or let's say engaged. Okay, then what does he do? He looks at his list of preferences. So remember that each man also has his list of preferences. So let's say he gets a new proposal from W1, and if in his preference list W1 was more, if he prefers W1 more over W to whom he is currently matched, what he will do is he will break this proposal, reject W, and accept the proposal of W1. So okay, and then the next step is that we keep on repeating. Okay, so is the algorithm okay? So what did we say? What happens is that every woman proposes to a man she has not yet proposed to, and what does the man do when he gets the proposal? If he's single, he accepts it. If he's already engaged to someone, if he prefers the other woman more, he's going to accept it. Okay, and then we keep on repeating this, and the claim is that uh, we're going to end up in a matching at the end of some number of iterations, some finite number of steps. We're going to end up with a stable matching, so or a stable marriage. So yeah, can I take some 7 minutes? uh,
Okay. Yes. This
okay, thanks. So I'll take one example. So I have a list of 4 women and 4 men, and they have some preferences here. So yeah, so let's say these are 4 women who have preferences. So we are, for the sake of uniformity, we are saying that uh, I mean, they have to write the name of each person at least once. So yeah, so each of them have their own preferences, and these are the main, and they have their preferences for women. Now what we will do is we will run the Gale-Shapley algorithm on this, and we will see whether the output is indeed a stable marriage. So yeah, so according to the algorithm, what happens in the first round? In the first round, what happens is that uh, she is going to propose to the first person on the list. So that is Dilip. So what does Dilip do? Dilip in turn accepts, because he is single, so he is going to accept. So in the first day, what happens is Shobana is matched to Dilip. What happens to Sheila? Sheila also proposes to the first person on the list, so that is Anup. So let's say Shobana is matched to Anup. Then Kavya does the same. She okay. Then Kavya does the same, and she proposes to Dilip. Okay, but what is the problem here? Okay, so I'll mark it. So Shobana is currently matched to Dilip, and Sheila is matched to Anup, and Kavya proposes to Dilip. But the problem here is that Dilip is already engaged to Shobana, whom he prefers the least, but he is engaged to Shobana. So what he does is he looks into the list, and because he prefers Kavya over Shobana, he is going to accept the proposal of Kavya. So yeah, so at the end, what happens is Kavya is engaged to Dilip, and this proposal is rejected. So now Shobana is single. Okay, and Priya does the same. Um, yeah, so Priya again proposes to Dilip, and what does Dilip do? He looks into the list, but Priya, he prefers Kavya over Priya, so he does not accept the proposal from Priya. Then what does Priya do? She proposes to Anup, but Anup. Okay, so maybe you can try this out. So currently, Anup is engaged to Sheila, but when Priya proposes to Anup, what should um, what would happen?
He will accept the proposal from Priya.
Exactly. So he accepts the proposal from Priya, and Sheila is now single. Okay. So this is what happened at the end of round 1. Now in the round 2, again the same process starts. So I think I'll move this. Okay. So let's. Okay, sorry. Okay. So let's. Yeah, let's repeat the process now. So next time what happens is, uh, yeah, Dilip has rejected. So now Shobana proposes to Nasir, and what happens now? So does he accept?
Yes.
Yes, because he is single, so he accepts the proposal. Then yeah, then Sheila proposes to Nasir. So but Nasir is already engaged, so let's look at Nasir. He is currently engaged to Shobana, and yeah, when Sheila proposes, Sheila is here. So does he accept or does he reject?
He accepts.
Yeah, so he accepts. So now Sheila is engaged to Nasir, and Shobana is again single. Now, yeah, and Kavya and Dilip are already engaged, so yeah, so we leave these two pairs as it is. Now, in the third round, so this was round 2. Now, let's do, um, yeah, let's do the third round. So, what happens in round 3?
Shobana proposes Mohammed.
Yeah, Shobana proposes to Mohanlal and he accepts because he is single. Okay, so at the end of 3 rounds, so now there are no single pairs, so nobody proposes and the algorithm stops here. So this is the matching that the algorithm ends up giving. So what I want you to observe is this matching stable or not? So is it possible that two pairs can, I mean, swap each other and be happier rather than being in this matching? So maybe you can take a minute and see. Okay, so yeah, so it indeed happens. It so happens that this is a stable marriage. So there are no instabilities in this marriage. Now, what? Yeah. So, um, what we will do is we will prove that the Gale-Shapley algorithm indeed outputs a stable marriage. So this is the claim, and the proof of this is very. I mean, it's very simple to state, but it's kind of not very intuitive. So let's see if it makes sense for you in one go, it's fine. But even if not, it's okay. I just want to say that this is a different kind of algorithmic strategy. I mean, it's different from what you might have seen earlier, and the proof of it is also simple, but it's subtle. So yeah, so let's we want to show that there is no unstable matching, um, unstable pair. So what we will do is we will assume that, let's say, there is a suppose, so this is a proof by contradiction. Suppose there is an unstable pair. So let's say m1 is matched to w1 and m2 is matched to w2 by the algorithm, but suppose m2 prefers w1 over w2 and w1 also prefers m2 over m1. So now what we want to argue is that such a situation never arises according to the algorithm. So suppose yeah so yeah so m2 is the one who is going to propose. So in this list, w1 comes up before w2. So before ever proposing to w2, m2 must have proposed to w1. So first point is that m1 proposes to w1 before w2. Okay, so this is because simply because they are preferring. Okay, sorry, read this as, I've changed the. Okay, so please read this as w2. Okay. Okay, so yeah, so before yeah, so in this case what we did was that women were proposing, so W2 proposes to M1 before she proposes to M2, because M1 occurs before M2. So at that point there are two possibilities: either M1 is single, or M1 is already matched to someone. So let's say M1 is matched to some W. Okay, so can it be that this W is okay? So okay, just a minute. So do we have some time, or is there some class?
We are free, ma'am. IT students.
Oh, okay. So yeah, so I'll just continue for 2-3 minutes. If you have, if CS people, if you have something, some constraints, then it's okay. I'll upload the recording. So feel free to leave. But yeah, if you want to stay, you are welcome. So yeah, so there are two possibilities. Either M1 is single, or M1 is already engaged to some W. So if M1 is single, what will happen?
He will accept the proposal.
He will accept the proposal. So in that case, M1 gets engaged to W2. And if M1 is already engaged to W, what can happen? Yeah. So he will accept only if W1, he prefers W1 over W. So in any case, M1 is matched to someone with a higher preference than W2. So M1 is matched to some W where W prime is of a higher preference than W1. So in either case, what happens is, now suppose M1 is matched to W2, and at a later point if W1 proposes to M1, then yeah, then is he going to accept the proposal from W1? You can use the chat if yeah. Okay, so yeah, in this case, M1 is not going to accept proposal from W1, because he prefers W2 over W1. So because of this, it cannot happen from here. You cannot ever reach a state where M1 is matched to W1. So this case just cannot happen. Using the same idea, you can argue for this case also. If M1 is matched to some W prime whom he prefers more than W1, then he's never going to accept the proposal from W1. So again, from this situation also, you cannot reach a state where M1 is matched to W1. So it's a simple argument, but it's maybe difficult to get hold of in the first course. So you can, I'll send you the link for the video. So it's nicely animated and everything, so you can take a look at it. Or if you have anything to discuss, you can let me know in the group also. So that's basically a very small argument. So what we said is, suppose there is an unstable pair, and then we argued that such a situation can never occur if you proceed with the Gale-Shapley algorithm. So yeah, so I think, yeah, that is all I wanted to say about this. Tomorrow, if yeah, tomorrow will be the final class, and we will look at a different problem. So it won't be related to matchings in particular. So we will see that tomorrow. Yeah, if there are any questions about what we discussed today, please, I'll stay here for a while. So okay, let me stop the recording.